Today, we are diving into something super specific and incredibly useful. Consider me your personal, enthusiastic study buddy because we're going to break down Chapter 17.6 of the Computer Science Field Guide, all about Agile software development. Our goal today? To literally explain this material word by word, concept by concept, so you can meticulously understand it and absolutely crush your final exam. We're taking that dense text, structuring it, and locking it straight into your memory. So, grab your notes and let's get into it. Here is our game plan for this explainer. We'll start by setting the baseline with the big Agile picture. Second, we'll dive into smart Agile coding practices. Third, we'll look at testing and refactoring code. Fourth, we'll explore the human element with people, customers, and courage. And finally, we'll wrap up with a really surprising historical twist in architecture meets software. Okay, part one, the big Agile picture, setting the baseline. Let's actually define what we mean when we throw around the word Agile. So what is Agile really? This process has completely taken over the software industry over the last 10 years or so. You've probably heard of specific frameworks like XP or Scrum, but for your exam, the absolute core definition you need to memorize is this. Agile is all about being extremely flexible and adaptive to change. Instead of mapping out massive, multi-year timelines, Agile teams work in really short bursts. We're talking 2-week iterations where they analyze, design, build, and test all in that tiny window. Now, there's a pretty stark, fascinating contrast between the old, standard way of doing things and the Agile way. Standard software processes lean heavily on documentation. They try to strictly manage and control any changes to the original plan. But Agile, it flips that entire concept on its head. It ditches heavy upfront planning because, well, the core philosophy is that things are inevitably going to change anyway. Documenting a massive master plan that's just guaranteed to become obsolete in a week is a total waste of time. Definitely commit that contrast to memory because it's a classic exam question. Moving right along to part two, smart, agile coding practices, writing the code. Let's shift from that high-level philosophy down into our first bucket of specific agile principles. First up, we have pair programming, and it's exactly what it sounds like. You've got two programmers, but only one computer. One person writes the code, while the other is looking right over their shoulder, actively hunting for bugs or edge cases the typist might miss. Now here's a totally counterintuitive concept that examiners love to test. Your gut instinct probably says, wait, isn't that horribly inefficient? Shouldn't they just work on two computers and type twice as much code? Nope. The reality is that finding and fixing bugs later on is an absolute nightmare. Because 4 eyes see more than 2, catching small errors right in the moment makes pair programming significantly more efficient than everyone flying solo. Principle number 2. I honestly love saying this one out loud. Y-A-G-N-I. Yagni. It literally stands for, you ain't gonna need it. This principle forces developers to keep things relentlessly simple. It's so tempting for a coder to think, hey, we might need this awesome feature in 6 months, I should probably just build it now. Well, Yagni explicitly forbids that. Since Agile expects constant change, building features for the future is a massive trap. Odds are the requirements are going to shift and you literally won't need it. Just build what you need right now. All right, part 3. Testing and refactoring code, building the safety net. How do Agile teams actually manage all this rapid change without losing their minds? Well, that brings us to one of my absolute favorite concepts, test-driven development, or TDD. Think about standard development. The logic seems obvious, right? You write the code, and then you test it to see if it works. Agile says, do the exact opposite. You write the test before the functionality even exists. Naturally, the test fails right out of the gate. But doing this forces you to meticulously think through the exact requirements and the special cases first. Only after you have a failing test do you write the code to make it pass. This is a massive trap question on finals, so really make sure you understand that order of operations. And for test-driven development to actually work, it has to go hand in hand with our next principle, which is constant testing. Agile processes take testing incredibly seriously. We're talking about massive suites of automated unit tests that run at least once every single day. That daily automated safety net is literally the only reason these teams can make such crazy frequent changes without just destroying the whole system. If a new change introduces a weird bug, boom, the daily automated test catches it instantly. Which leads perfectly into our next principle, refactoring. Remember Yagni, how you just build the simplest thing possible for today? Well, as the project grows, that super simple design is going to get pretty clunky. Refactoring means you open up that code and completely overhaul its internal structure, but without changing what the program actually does on the outside. And how do you know you didn't accidentally break its behavior? Exactly, those automated unit tests we just talked about. They verified that the code behaves exactly the same way before and after you messed with it.
The Fields Guide drops a fantastic analogy here that you absolutely need in your back pocket. Quote, imagine that when building a bridge, you started off by doing the simplest possible thing, putting a plank over the river, and then continually refactored the bridge to get the final product. End quote. That really highlights why refactoring is completely unique to software. If you tried to build a physical bridge like that, it would collapse immediately. But software is soft, it's flexible. You can throw down a coding plank and just continuously refactor it into a massive Golden Gate Bridge over time.
Okay, moving to part 4, people, customers, and courage, the human element. Because software isn't just about machines, it's deeply about the psychology and the people building it. 40. That is your magic number. This principle is known as programmer welfare, and it flat out states that 40 hours is the absolute maximum an Agile developer should be working in a week. If they pull overtime one week, they are strictly forbidden from doing it the next week. And honestly, this isn't just about being nice to your employees. It's a highly calculated business strategy to dodge burnout. Writing software takes intense creativity and heavy problem solving. And frankly, a tired, burnt-out programmer writes terrible code. Next up is customer involvement. In a standard setup, a customer hands over a list of specs, cuts a check, and then sits around for 5 months waiting for the final delivery. In Agile, the customer is ideally treated like a full-time member of the development team, giving constant, daily feedback. Now, I know what you're thinking. Hiring an expert, like a literal doctor for medical software or a teacher for educational apps, to just sit with coders all day sounds wildly expensive. But in practice, it's a massive money saver. Paying one expert's salary is peanuts compared to blowing millions of dollars on a failed software delivery just because you didn't get their feedback until month 5. Principle number 8 is courage. Now, courage might sound like kind of a touchy-feely, emotional word for a computer science exam, but it is an official, vital coding principle. Because Agile demands constant adaptation, programmers have to have the guts to jump into highly complex code, often code they didn't even write, and radically change it, or even just throw away bad work entirely. Changing complex systems is terrifying, but you can have that courage entirely because of that safety net of automated unit tests. You can be brave because those tests will catch you if you fall. And that brings us to part 5, architecture meets software, surprising origins. Let's see how all of this builds up to a brilliant little piece of history, one that is absolutely perfect for grabbing some bonus points on your test. So who is Christopher Alexander? We just talked about how software isn't really like building physical bridges, right? But ironically, it draws huge inspiration from physical architecture. Christopher Alexander was an actual building architect who fundamentally shaped Agile software development, entirely by accident. He pushed this idea that you must deeply involve the customer in the design process of a building. Well, the software community read his stuff and just completely absorbed his suggestions into what eventually became Agile. The best part? Christopher Alexander knew literally nothing about software development. He was absolutely shocked to find out he was a legend among coders. Okay, we've covered a ton of ground, so let's do a rapid-fire review of all 8 core principles to meticulously lock this in for your final. 1. Pair programming. 4 eyes are better than 2. 2. Yagni. Keep it simple, only build for today. 3. Constant testing. Run those automated tests daily. 4. Refactoring. Safely improving the code structure. 5. Test-driven development. Always write the test before the code. 6. Programmer welfare. 40 hours max. 7. Customer involvement. Get that full-time feedback. And 8. Courage. The bravery to boldly adapt the code. And there you have it, the Computer Science Field Guide, Chapter 17.6, totally decoded and structured perfectly for your study session. Before we wrap up this explainer, I want to leave you with a quick provocative thought. Now that you actually know the inner workings of these 8 Agile principles, take a look at your phone. How do you think these exact concepts, things like constant iteration, automated safety nets, and programmer courage, are actively shaping the apps and software you rely on every single day?